a single fiber. So that DWDM tunable SFP plus is kind of a big deal.
Yeah. It also, as a vendor, it's our favorite product because it's the least like amount of risk to stock. It's if we have to stock one of every channel, and I know that you guys have to deal with this too. It's you never know if you're going to end up using it, but if you know you're going to use a DWDM at some point, having that flexibility definitely takes away some of the stock risk for sure. Since you brought up the DWDM tunable, I figure it might be a good time for us to kind of transition into that discussion.
Sure.
That works for you? Yeah.
Yeah.
So first, just wanted to, what is DWDM versus CWDM and wideband? I know I went backwards there. So wideband, just as kind of mentioned earlier, the data sheet will say average wavelength of 850, 1310, or 1550, but that wavelength can really drift plus or minus about 20 nanometers. And unfortunately, why is this an issue? Well, you're kind of limited in what you're actually able to put on a fiber. So if you design a network doing wideband, like optical signals, you're getting about 1 to 3 channels on a fiber. Now, the great thing about this is relative cost is low. There's not a whole lot of smarts put into the transceiver in order to stabilize the wavelength. But as you get into CWDM and DWDM, you need newer components to kind of stabilize, and that drives the cost up. Tunable availability with wideband is not really applicable. CWDM, we get asked this all the time, and it's not capable. And then, with DWDM, yes, it is capable. So real quick with the CWDM, it took the concept of wideband where you had plus or minus 20 nanometers and shortened that band by about to plus or minus 6.5 nanometers. So the channels themselves are physically spaced about 20 nanometers. So when you talk about CWDM, it's a channel 43 for 1430, a channel 45 for a 1450. The optic that is actually being plugged into the 1430 is transmitting from about 1423 roughly up to about 1436.5. And so it never overlaps with the adjacent channel optical signal. And so basically the concept behind all of this between wideband, CWDM, and DWDM is to create a transmit technology that enables you to add more wavelengths to the same fiber. And by adding more wavelengths to the same fiber, you get a lot more data being able to be pushed through. So I say DWDM max capacity of like 160 channels. Most operators limit it to about 40 channels. It's capable, but 40 seems to be about the limit. So back to the whole tunable discussion. With DWDM, you have two different types of transceivers. You have the fixed channel DWDM and the tunable DWDM. The fixed channel, those that don't know, that is an optically locked SFP. When you order it, you're gonna order it to a very specific wavelength, and that's gonna be the only wavelength that you're gonna be able to use that transceiver for. Tunable DWDM gives you, the operator, the technician, whoever's working with it, the capability of changing it to whatever DWDM channel you need. I think Comcast primarily uses 14 to 61.
I'll take your word for it.
Yeah. All right.
But that sounds right.
That sounds right. Another question we do get asked quite a bit is, are fixed channel and tunable transceivers interoperable and or interchangeable? Yes, but there are some things you got to consider. One is fixed channel and tunable DWDM transceivers are interoperable, assuming the tunable transceiver is tuned to the same wavelength as the fixed channel transceiver. Additionally, fixed channel and tunable DWDM transceivers are also interchangeable, assuming you're using like for like hardware from a link budget perspective, and the tunable is properly tuned. I do need to make a correction here. That first statement I made, saying that it's tuned to the same wavelength, that's talking about if you're replacing a tunable transceiver from, or you're replacing a fixed channel with a tunable, making sure that tunable is coded to the same wavelength that the fixed channel was.
Right.
The receivers on the on DWDM SFPs are wideband receivers. They'll accept pretty much any DWDM channel. So you don't have to have like matching pairs on each side. The receiver typically accepts anything from 1525 nanometers up to 1575.
So there are pros and cons, right, to all of them, whether it be distance, cost, flexibility in tuning. So there are, a lot of different options available based on the need of your particular application. So thank you though for running us through all of the variations, or I think we've gotten through all the variations. It was kind of a lot in
Yeah.
in the SFP and SFP plus space, and a couple others. Okay, so what's next?
Let's do the techniques for overcoming data rate and distance challenges. Does this sound good to you?
Sure.
All right. So techniques for overcoming data rate and distance challenges. One is adding optical lanes to the same form factor, or to at transceiver. So we saw this with QSFP and QSFP 28s, and we are seeing this with some of the newer QSFP like 400 gig technology, where what's kind of funny about those is like the 400 gig SFPs are 4 SFPs crammed into one 2 times. So that, like, you'll see DD, it's dual density. So not only are we adding SFPs, but then we're doubling how many SFPs we're adding to the same form factor.
So it's
So
dual density and quad.
and quad, yeah. So yeah. The other one, another technique is PAM4 modulation. On the next slide, I'll have a pretty good visual that explains a little bit of the difference between NRZ and PAM4. So PAM4 stands for pulse amplitude modulation. The number 4 stands for the number of levels. That'll make a lot more sense on the next slide. Another one is forward error correction. So this is where a portion of the bandwidth is dedicated to error correcting code meant to assist the receiver with interpreting noisy or unreliable data. Basically, what forward error correction is just a very fancy algorithm that the host device determines how to interpret the data. It's not something that's actually managed by the transceiver, but it's rather the 2 host devices talking to each other before data is being transmitted over.
Do you know if that's similar to like the Reed-Solomon digital error correction in digital RF?
Actually, you hit the nail on the head. Yeah, actually, one of the FECs that's used in the industry is a Reed-Solomon FEC. They were almost like one of the pioneers in this sort of space.
Yeah, error correction using parity bits. Ron Rannick wrote a really good article on that one. I think it was called "What's a Code Word or Two Among Friends." That did a really good job of describing read error correction. That hopefully one of these days I'll get him on the show and we'll revisit that document. But as for some of us that are in like the DOCSIS 3.1, DOCSIS 4 world now, There's a different type of error correction called low density parity check in OFDM and OFDMA, but Reed Solomon is the old standby in digital signal decoding and error correction.
Yeah. There's a million different types of FEC, and one thing to be mindful of is you have to have FEC matching on both sides of the link. Which, yeah. Also, the use of FEC, we see in some 100 gig optics for the longer, pretty much anything over 40 kilometers at 100 gig is going to use some variation of FEC. But when we make the jump up to 400 gig, every optic in 400 gig uses FEC, even the short range, short reach.
For standards, training, certification, events, even membership. Everything you need to know, SCTE.org.